So today I want to kind of do application of Ampere's law. And let's start with what we know about it, that it's mu naught I enclosed. And then we have the integral side, which is the line integral of b dot ds. And yes, I sat in my garage this very morning, said I was going to grab something to bring to school today so I could show all of you, and then promptly forgot what it was, grabbed something else that I didn't need, which is in my backpack right now. And I'm like, why did I bring this to school? So not always operating on all the cylinders at home, so that's the way it goes. But I intend to bring my my amp meter, my Amperian amp meter to school so you guys can see it. It was my dad's too, which is even better because I have a little nostalgia for tools that my dad gave to me. Yeah.
It's not too much of a side tangent. How do you measure?
So I want to be clear. Ampere's law, like Gauss's law, has limited uses because we can only use it in circumstances where we understand the symmetry. Now, I say that, but also understand that it's like Gauss's law, that there are other ways to use the law that are less interesting from a mathematical perspective, but are certainly ways in which the intention of the law has been meant to be used. I'll remind you that just like Gauss's law, which I know I keep making the comparison, but I think it's a good comparison to make because, for one, it was last semester, and I don't want you guys to forget about it because we're going to be needing to do some review on it. Remember that there were problems with Gauss's law that had nothing to do with finding the electric field, that they were all about being able to find how much charge was maybe located inside a surface. So they would ask questions like, what is the flux through this surface? And they would have a couple of charges, say a positive charge here, a negative charge here, a positive charge here, and they'd say, okay, I've got this surface, and I have this surface, and I have this surface, and I have, let's get one more. And I have this surface, and I'd say, which of these has zero flux? Do you remember those kinds of problems? Or, which one of these, has the highest amount of enclosed charge? The questions like that, but they usually phrase it about flux, and, you would look at this and say, well, if I wanted the one that had zero flux, well, it's not the blue one. It can't be the white one, and it can't be the red one. It has to be the one where the flux is zero, and we're actually looking at this side to determine it, which one has the enclosed charge of zero. And the only one that would be the green one. Do you remember those kinds of problems? So you understand that there are the same problems, except I take those things and say they're not charges, but I say that they're all currents. And so I have a current out of the page, and this current's into the page, and this current's into the page. And I ask the same question. I say, which one of these has the smallest line integral related to the magnetic field through that loop? Do you understand why they would ask it that way? They're not asking about the enclosed current purposefully to try and force you to think of this b dot ds, but they are referencing the enclosed current. So they will describe this as just the line integral of the magnetic field, which is all it is. It doesn't have a special name outside of that. So when dealing with Ampere's law, we found functionality in trying to use it to find the size of the magnetic field, but there's other functionality to the law outside of that. And one further thing, there's something that's going to be added here that's going to have some interesting dynamics. And that point that's going to be added here changes the nature of what Gauss's law is really about. What Ampere's law is really about. So there's a future that has interesting things regarding Ampere's law. We generally use it as a means of finding the size of a magnetic field within certain kinds of geometries of currents. So the first geometry we did was the long straight wire. That was the first introduction to how we would use Ampere's law. I want to give you the next two uses of Ampere's law that are directly applicable. And just remember from last year, or from last semester, Gauss's law had three really direct applications: the point charge, the line of charge, and the sheet of charge. Do you remember those? So there's going to be similarly 3 applications of Ampere's law that we're going to think that are relatively important. And in the same way that I suggested you memorize things like the line of charge electric field and the point charge electric field and the sheet of charge electric field, some of the results we're getting here I would also encourage you to memorize. And just so you know, I have assembled a list of all the things I think you should memorize that I'll probably just post out there as an announcement someday, because as we get closer to the exam, I'm going to want you guys to have some skills that you can rely on and be really fast about, and those memorizations are going to be helpful. So I want to start by taking a look at a single loop of charge for a minute and remind us a little bit about the dynamics of a single loop of charge. I'm sorry, I keep saying loop of charge. A single loop of current. I want to remember the dynamics of a single loop of current. So I have a loop of current, and I've kind of turned it sideways, but it has a radius of r. You'll remember that there's a magnetic field that is created due to this loop of current. When we found an expression for the strength of that magnetic field at the center, but we can't use Ampere's law for that because we don't have the uniformity required to use Ampere's law. The magnetic field around any Amperian loop here would not be uniform, and therefore there's no way for us to do the line integral, at least no mathematical way that I've ever seen. But based on the direction of this current loop, and I'm thinking this side is closer to us and this side is further away, that all okay? If that's true, then I think the magnetic field passes this way through the center of this loop, because I think I have a little thing going around like that, and on the other side it's just the opposite, and therefore through the center we have a magnetic field that direction, and we know the size of that magnetic field is mu naught I over 2r, where r is radius. This is the magnetic field of a single loop. Can't use Ampere's law for it. Now, it occurs to me that part of the reason we can't use Ampere's law is because this single loop it's spread out. And if we look at it in the top, like this, we know the magnetic field is due to the contribution of all of these moving charges in this circle. But the magnetic field here isn't the same as it is here. And although we could probably assume that it's the same size as it is here, here, and here, it varies all around the inside of that loop. This inside the loop is not a uniform magnetic field. We just used the fact that being in the center meant we were equidistant from every piece of current, which allowed us to use Biot-Savart as a way of calculating the magnetic field there. And we just used the symmetry and that, but we could not find the magnetic field here, not easily using Biot-Savart, because for every single piece of ds that we have, our distance is different and the angle is different. Now, that would be a much more challenging calculation to make. I'm not saying you couldn't make it, but even right now, if we wanted to set it up, do you know offhand the relationship between the angle here of dr and the angle of the tangents for every part of a circle if you are not at the center of a circle? I mean, there's a way to get it. It's not particularly hard, but I think it's outside the mathematical skill set. So there is something that's been noticed by people, and I'm going to be very careful to draw this. So I would like you to be careful too when you draw it, and it's worth taking some time to draw. If we take and make a coil of wire, we might be able to use the amplification of the magnetic field and the repetitiveness of all those wires to help straighten out and reinforce the magnetic field through the center. This has a name. It's called a solenoid. And solenoids help straighten out the magnetic field and collimate it. I'm gonna draw a cutaway of this solenoid. And I'm gonna take some time to make it look nice. I would encourage you to do something similar in your notes. And to help me, I'm actually gonna give myself a bit of a guide line that I'll erase later. Just something to help me make my circles. I'm gonna make circles that represent the cutaway of the wires. And then I'll make a second set right below, like that. What I'm trying to do is take and just make a cutaway of a solenoid. So I'm kind of cutting it in half and looking at the wire. So imagine that current going in here, coming out here, and going in here, and coming out here, and going in here, and coming out here. It's a coil of wire. They're all stacked up on each other. You follow what I'm doing here? I'm going to make into the board at the top. So current I is going into the board at the top. And out of the board at the bottom. So every one of these loops has the same current in it. What we've done is just have them tightly packed. Now, just looking at one of the loops, and I'm going to pick just one of these to look at. Let's look at this one right here. I'm just pick one of these loops. I'll pick another one on the top to look at. That loop has to be producing a magnetic field. And we know just that single loop produces a circular magnetic field that gets weaker the further away from the loop we are. So based on the right-hand rule and the fact that this current is out of the board, my magnetic field is going to be this way due to that loop. Everybody follow that okay? Any problems with that? All right, so we're gonna do this. I'm gonna do the same thing up here for this top one. I'm using blue to differentiate where these two fields are coming from. But this one is into the board. So the magnetic field will curve in the opposite direction. Now, you do see that these are complementary magnetic fields from both sides. But we also get this reinforcement action that's also happening at the same time. Because although we have magnetic fields coming from, we're just drawing this one, you do know that there's got to be the same thing coming from the wire directly adjacent to it. Do you understand what I'm saying? That each loop is compounding the size of the magnetic field. Let me show you what I mean, I guess. So the wire right next to it has a compounded magnetic field, just like that. although I didn't capture all of what I wanted to capture there, so I'm in trouble. So let me just draw it like this then. Every one of these wires has a circle that looks like this around it, right? A magnetic field that looks like that. So the next wire over, there's a circle just like that for magnetic field. That's the same size and in the same direction. Yeah.
Is this what like shows and stuff mean when they say a coil gun?
I don't know what a coil gun is. So I don't know what shows you're watching that have coil guns.
Use it interchangeably with rail gun.
Don't know. Sorry. Now, you do see the reinforcing effect of all the coils, correct? It can be shown two things. First, this reinforcing effect makes the magnetic field inside the solenoid relatively uniform from this point all the way to this point. It straightens out the magnetic field lines. It does more than just that too, because if you continue to look at this, draw one more circle that's bigger, and realize that although we still have magnetic field outside, the magnetic field up here is in opposition. Do you see that? Outside the solenoid, the blue is going to the right, but the red is going to the left. And similarly, if I draw a big one to represent the magnetic field coming from the top and pinch it on the bottom, the blue is going to the left while the red is going to the white. What you get is basically magnetic fields that are nearly zero on the outside of the solenoid and concentrated magnetic fields through the inside of the solenoid. But like a capacitor, you get this if you can make lots of loops and make your solenoid long compared to its width. The smaller you make your solenoid, meaning the fewer loops you have, the less uniform the magnetic field will be. Go ahead.
What are the magnetic fields?
Although at the end of this, I don't exactly recall. I'm sure that I saw the clock and realized we only had a little bit of time, and I wanted to impress upon us what we had to do here. So let me remind just a little bit about what we were doing. This is a solenoid, which means we're talking about coils of wire that are wrapped around. Usually you wrap it, well, we're going to be making one for a lab tomorrow probably, so they'll be easy for you guys to make one. But the point of a solenoid is, of course, to try and collimate a magnetic field, to get some kind of uniformity in that magnetic field. And in doing so, we're using Ampere's law to get an expression for what the size of that magnetic field would be on the inside of the solenoid, assuming a lot of things that may not be exactly true. And one of those things was that I don't know that the magnetic field inside of there will be perfectly collimated. To do so, we have to make some assumptions, and one of the assumptions we had to make was that this distance, how far apart the radius of the solenoid, was small relative to how long the solenoid is. So if we can make those kinds of reasonable assumptions, then we might be able to take a small subsection in the middle and wrap an Amperian loop around it, and from there determine what the size of the magnetic field would be. To do so, we have to pick a direction to go, and I've probably labeled this poorly for an actual direction. So let's try going in the direction of the magnetic field. That might make more sense. So I'll put A here, and then B, C, and D. So now I've kind of labeled a rectangle, and it has to be a closed loop. So that's what this circle means here. That's our closed loop. But we're going to go through and evaluate each segment. And we'll start by looking at A to B. Now, in looking at A to B, it's a line integral. And although I zoomed in, I remind you, it's B dot ds. So we're evaluating first whether there is a magnetic field in that region, and if so, what is the direction of the magnetic field relative to the direction that we are going around the loop. We are currently traveling this way around the loop. But I'd argue that it's different in this region than it is in this region. Would you guys agree? There's no magnetic field here. So there would be no contribution to the line integral here. However, here, I would say that there's also not a contribution to the line integral because it's a dot product. And for a dot product, we have to evaluate the cosine of the angle between the two vectors, and they are perpendicular to each other. Do you guys see that? Is that a yes or a no? Because I want some authentication. You can see that B is going that way and DS is going that way. We good? So that suggests that the cosine evaluation, the dot product evaluation in this section would also be 0. You all follow that okay? You sure? Because you might be asked this. So can we also agree that we're going to have the same argument over here from C to D? So no contribution to the line integral for the magnetic field passing in the loop. So let's go through and knock those out. So A to B, 0. And C to D, also 0. Now that leads us B to C and D to A. Well, D to A will be really easy. D to A is outside of the solenoid where the magnetic field is 0. So I think D to A we can also wipe out and say is 0. That leaves only the evaluation of B dot ds. First, if we're traveling in the direction of the magnetic field, meaning if we're traveling along ds in that direction, we are traveling with the magnetic field. That sounds like the cosine will be the cosine of 0 degrees. We don't know the size of the magnetic field. We'll just put B here. But we are evaluating an integral, and every piece of B is the same value in the direction of ds. So what's left is just the integral of ds, adding up all of the length from B to C. Can we use the fact that it's L long as what we're going to use as our sum? So I'll just put the L right there. B times L times the cosine of 0 degrees. Any questions? All right. So we've done the right side of our Amperian integral, and we have successfully added up all of the B dot ds, the line integral for magnetic field and length. Let's do the left side now. We know this is going to be BL, that's it. Cosine of 0 degrees is just 1. Mu naught I enclosed. I think mu naught goes without saying. I enclosed. I think I enclosed will be whatever I is times the number of loops enclosed. I could put count 1, 2, 3, 4, 5, 6, but you understand that that's just an arbitrary drawing. It's really just going to be I times the number of loops. That all okay? Any question about where that n came from? Because I made it up on the spot. Yeah.
I don't really understand I enclosed. Is it like the amount of charge in that area?
How much current passes through the loop?
In a second?
Current is charge per second. It's just how many amps of current go through the loop. So each one of these wires carries I worth of current.
Okay.
Is that okay?
Yeah.
So whatever number of loops I've enclosed in my Amperian loop times the amount of current in each loop. Is that okay?
Yeah.
All right. So if I want to use Ampere's law to figure out the size of the magnetic field, I've got it right here with things that I think make reasonable sense for the size of the magnetic field. So solve that for B, and I'm going to regroup it just a little bit. Mu naught times I times the ratio of N over L. this is the equation for a solenoid. Sometimes written with a lowercase n replacing this, but I think it's best you just know it n over L, because it's what's known as the loop density, the number of loops per meter. Loop density, number of loops per meter. They'll often express, I have a solenoid with 300 wraps per meter. They're telling you something very specific about how to deal with the wire density. So a solenoid really has its magnetic field based on how much current there is and how tightly you can pack the loops in that region. That's how you build a solenoid. Now, solenoids are just simple devices that generate a magnetic field, but they generate it on command. That magnetic field exists when there's a current passing through the loops. It completely disappears when the current dissipates. So, pretty simple to build. Your solenoids that you're going to build tomorrow, you'll have small forms that you're going to be using for them. They're just PVC pipe. And we're just going to look at the deflection of a needle on a compass to kind of get an idea for the size of the magnetic field. In fact, we're going to do a lab with that to try and measure the acceleration, the size of the gravitational field of the Earth. And we're going to talk a little bit about that lab here in a few minutes. But this is kind of how Ampere's law works. This also, keep moving this around. This equation also, one of those things I'd probably tuck away next to the other two that I've talked about so far this year. They're not on the equation sheet, and you don't necessarily want to have to do this every time they call up a solenoid. So it might be worth memorizing the equation for a solenoid. And since we're doing a bit of a summation, I'm going to pick two people. Actually, I only have to pick one. Which one of these is for a single loop? Don't answer. I'm going to pick somebody. We're going to see who's paying attention this morning. So you're going to tell me which one of these represents a single loop of current. All right. Since Allie gave us that one, the next question is, which one can be solved for using Ampere's law? The long wire or the loop? Meaning, which one can you prove using Ampere's law? Ali? Long wire can be proved using Ampere's law. You can do it the other way, but is it any fun? Not at all. And of course, this one is the only way to do it is Piazzavar. All right? Memorize. Okay, I pointed out, I'm saying it again, memorize. Tomorrow, I might call you up on that. Do you understand my meaning? Quick quiz, right away. You either know them or you don't. And don't assume I'll have them sitting on the board nice and convenient for you. All right? This is known as a toroid. So the other one's a solenoid. This is a toroid. T-O-R-O-I. Toroid. That's another way to make a magnetic field, another way to collimate a magnetic field. Toroids are used in nuclear fusion. They can be used to help suspend a plasma and to allow that plasma to move at velocities inside the toroidal shape, with the hope being that you'll get enough collisions to cause fusion reactions to occur. Plasmas are too hot to come in contact with their container, so you have to find a way to keep them from coming in contact with their container because they'll melt it if they do. So I want you to see if you can come up with a means of using an Amperian loop to determine the magnetic field inside a toroid. There are a couple of specifications I want you to use. I want you to assume that there are two R's that represent the inner and outer radius. I don't know if they'll be important in the answer, because as you saw, how big a radius we have for a solenoid didn't come into the problem, as long as the radius was small compared to its length. So we have an inner and outer radius, and I also want you to assume that there is a fixed number of loops, n number of loops around the entire toroid. come up with an Amperian loop that could be used to figure out the size of the magnetic field inside this toroid, and use some of the discussion we've had about what would be reasonable assumptions. So I'm going to let you speak at your table, but go through the steps. You're using Ampere's law. U naught I enclosed equals B dot ds. This will not be a surprising answer. So as a vehicle goes, having a Amperian loop that goes through the middle, anywhere, will be fine. Now, that suggests that there's some things about that you'll need to probably use in your next portion, which is you'll need a value to represent the radius, perhaps. Because you're going to need some way of doing your calculation, your B dot ds. All right, so which side did you begin on? The right side or the left side? Ouch. What do you have to do on the left side? Yeah, find I enclosed. So we have I is the amount of current. What do we know? We know the number of loops. Will our Amperian loop encounter all of the loops? All right, so all you had to do on the left side was write I times N. There, we have the current enclosed in our Amperian loop is all the loops times the current. All right, right side's probably gonna be a little bit more challenging. But can you infer something about the likely direction of the magnetic field inside the toroid? So based on the way it's drawn on the screen, it's either clockwise or counterclockwise, isn't it? So I would argue that we just pick one. What direction do you think the magnetic field is? We don't know from the current. The current is drawn in an ambiguous kind of way. But can't we decide which direction we go around the loop? So if the magnetic field is clockwise, we'll just go around our Amperian loop clockwise. If the magnetic field is counterclockwise, we'll just go around our Amperian loop in the counterclockwise direction. Does that seem reasonable? So I'm going to say that we're going this way in our Amperian loop because we believe perhaps the magnetic field is this way inside our toroid. We don't know for sure because I have to use the right-hand rule and I didn't make it very clear which wire is which, did I? That was on purpose to make us think about that a little bit. But I mean, if the current's going this way, then my magnetic field would be like that, which would be this way through the loop. But again, if I guessed wrong, I would just go in the other direction with my Amperian loop. Fair enough? We don't have to think too deeply about it. You're using Ampere's law really for the first time today, so I think the first thing I'm going to suggest is that we say, all right, B times ds times the cosine of 0 degrees. That we will go around our Amperian loop in the same direction as the magnetic field. So now our next job is to find a way to sum up the contribution of the magnetic field in the direction of our loop. So I think I would probably just pick a small portion of the loop and call it, this is our ds right here. It's a small piece of arc length. I can either jump to the end and say if I sum up all the arc length, I'm going to get a circumference. Or I can break ds up into r d theta and start at 0 degrees and go around 2 pi. We've done this a bunch of times, so I don't feel like I'm really making this part too tough. Pick one. Do you want to just say that the summation of ds is 2 pi r? Or do you want to substitute in r d theta and integrate from 0 to 2 pi? All right, well, if you know what we're talking about, then you know you can say this is b times 2 pi r equals mu naught I times n. That's all there is here. There's not a lot here, but there's only really two ways to make a device that can amplify a magnetic field: toroids and solenoids. And the solenoid one is the most likely for a collimated field, because if you look at the answer here, you find that the magnetic field is not uniform. The magnetic field is stronger on the inside than it is on the outside. So there's things you try to do to try and increase the likelihood that the magnetic field is relatively uniform. You make these two numbers close together, right? That would help. So you make it very narrow and very much round, and you can get a relatively uniform magnetic field.